Hello and welcome to this special lecture about DFT models of grounded cognition. So I should mention maybe in the beginning already that the term grounded cognition is probably not well known, and in the course of the lecture it will become clear why it's called that and what it exactly is. But for now, I'd like to start by giving a motivation for this talk. So the long-term goal of the research program, which we subsume under this term grounded cognition, is the goal to build neural dynamic models of the higher cognitive competences. And what a higher cognitive competence is can best be understood by examples. So these are the kinds of competences that are usually associated with the uniquely human intellect. And they include things like language understanding. So when I utter a certain sentence, then your brain is able to understand what I'm saying, and it doesn't just process the sequence of words. So there's a lot more going on than actually just detecting which words were said or something like that. But really, your brain is able to to sort of think a thought expressed by the sentence that I'm communicating. So that's what we refer to by understanding what I'm saying. Another of these higher cognitive competences would be reasoning, and that can actually be subdivided into different kinds of reasoning. One of them might be called logical reasoning. So that would be drawing a conclusion from a certain set of premises. So if you are told certain facts about the world, and then you have to infer whether or not a certain conclusion is true, that would be called logical reasoning, or more specifically, deductive reasoning, going from a set of premises to a conclusion. Another type of reasoning is analogical reasoning, where essentially you observe or perceive a certain state of affairs, and you are able to come to the insight that that state of affairs is in some way analogous to another state of affairs that you have previously learned about. And this way you are able to infer certain conclusions about the current state of affairs by virtue of detecting these analogies and using your background knowledge from analogous situations to draw inferences in the current situation. And planning might also be subsumed under such a higher cognitive competence. So that would be you have a certain goal that you want to achieve, and you have to come up with a plan, a step of actions that you have to perform in order to achieve that goal. And there are, depending on who you ask, there are different kinds of competences that people would call these higher cognitive competences. Some are actually critical towards calling this a higher cognitive competence. So some people would just say there is no distinction between higher and lower cognition. There's just cognition, and there's no categorical difference. So that's why it's important to distinguish actually between a cognitive competence, which just says a certain, which just denotes a certain ability that you have, versus the term higher cognition, which relates more to the processes that give rise to these abilities possibly. And some people would say there's no such thing as higher cognition. The brain is just a single thing, and there's no boundary. And that's actually in line with what we believe also, that there's no boundary between the lower level sensory motor representations and processes on the one hand, and some detached faculty of the human intellect. So it's all sort of a single thing following similar principles, reusing neural mechanisms that are evolutionarily much older than the uniquely human intellectual competences. And the term grounded cognition is essentially it emerged to contrast it with another theory of how these higher cognitive competences come about in the brain that was quite widespread in cognitive science in the last century, and it actually has many proponents still to this day. And that theory is sometimes referred to as the classical computational theory of mind. Some people also call it information processing. It's sometimes a bit fuzzy what these terms mean exactly, but the classical computational theory of mind, that has a very specific definition. And according to that theory, cognition is understood as the algorithmic processing of symbols. And this, what algorithmic processing of symbols means is usually explained in terms of analogy with computers, or maybe more abstractly with Turing machines, if that means something to you, which are sort of abstract models of a computer, which have a memory and a processor and an internal state, and then they somehow operate on these representations in memory, and as a result they change their state or write something new to the memory and so on. So that's an abstract way to think of the computer. And generally what a computer does can be characterized by two things. So the computer is essentially a universal problem solver, which receives a description of a problem as a sequence of symbols, or maybe as a recursive data structure. So some symbolic representation of the problem is given through the computer. And then the computer performs a certain algorithm on these symbols. And by virtue of performing that algorithm, it solves a certain problem. And the classical computational theory of mind essentially states that that is analogous to how the human mind solves problems. So let's look at an example. So assume that we're given a deductive reasoning task. So we're given two premises here in this example. First premise being the Porsche is parked to the left of the Dodge. Second premise is the Ferrari is parked to the right of the Dodge. And then below this line here, there's a conclusion that could be drawn from these premises, namely, therefore the Dodge is parked to the left of the Ferrari. So this would be an instance of deductive reasoning, inferring a certain conclusion from a certain set of premises. And in the classical computational theory of mind, the idea would be that the human mind solves such problems by transducing the premises into a symbolic representational format, and then performing a certain algorithm on these symbols in order to infer a conclusion. So the premises could, for example, be encoded as this here. So the claim is not that we exactly encode it in this predicate calculus here, but this is just to give you a sense for what the assumption is, that there's some sort of symbolic representational format that represents the premises, and then some algorithm is performed in order to deduce another symbolically represented conclusion. And that's essentially then the account of how human reasoning works. And the motivation for this theory generally is that it can be shown theoretically that computers are universal problem solvers. So any problem that can in principle be solved by a mechanical procedure can be solved by a computer, or more abstractly by a Turing machine. And this then gives us the computer as a model of the universal problem solver. And now if we ask ourselves, how does the human mind solve problems so flexibly? Because the human intellect is actually marvelous. We're able to very flexibly solve very diverse kinds of problems. And it's been, well, it is a mystery how that actually works. And the classical computational theory of mind essentially has been put forward as a proposal for how this mystery is to be solved. Namely, the human mind is like a Turing machine. And that's how we achieve this flexibility. And this theory has actually given rise to a quite large research program that has been referred to as computational cognitive modeling, at least classically. These days, the term computational cognitive modeling refers to other kinds of cognitive modeling as well, not just to this classical computational theory of mind modeling. But in the early days of cognitive science, say in the 70s or so, it started as purely algorithmic modeling. So the idea was we want to scientifically study how the mind works, and we want to create models of how the mind solves certain cognitive, or how the mind solves certain tasks, and how can we make sense of the cognitive processes that can explain human performance at these tasks. And these models were then given as algorithms. So, for example, if a classical cognitive scientist wants to account for how does the mind achieve deductive reasoning, then they would propose an algorithm that does deductive reasoning, and that maybe can account for certain empirical data about how humans perform in deductive reasoning tasks. And that would then be a theory of how deductive reasoning works in the mind or in the brain. And I'm saying all of this not to convince you that this theory is true. I think it's very wrong, but I'm saying this because this theory has had a substantial influence on the field of cognitive science, and it still has many proponents today. So that what makes it relevant to look at this theory and to look exactly at where this theory is wrong, and why and what alternative proposals can be made which can account for the same kind of cognitive flexibility while being more biologically plausible. So even in the neurodynamics community, there's people who think that this is a sort of a high-level description of how the mind works, and the neurons or the neural networks of the brain, they essentially just implement these algorithms somehow. So there's a classical distinction between different levels of description in cognitive science, going back to Mars. So there would be the computational level that abstractly characterizes an algorithm that solves a certain problem, like deductive reasoning. And then there would be the implementational level that explains how this algorithm is physically realized. And the idea there is that the neural networks of the brain are just the physical substrate that implements the algorithm. And so there are very many neurodynamic modelers who actually try to come up with neural networks that implement certain algorithms, for example, via spiking neurons or rate neurons, or maybe artificial neural networks. And let's maybe zoom in a bit on what this theory actually entails. So we know a lot about how the sensory motor representations and processes of the brain look like. And the idea of this classical computational theory of mind is that these sensory motor representations are actually transduced into a completely new symbolic representational format. So when a human being, for example, perceives a certain scene, let's say a tree with apples hanging down from it, and he or she wants to solve some reasoning problem about that situation, whatever that might be, then the idea is that the perceptual representations, which somehow encode the scene in terms of the colors of objects and the identity of objects and certain textual features or whatever, and where they are located, that is transduced into a representational format which represents the various entities in the scene in the form of symbols. And these symbols are amodal, which means they are not identical to the perceptual representations that gave rise to them. but they bear no resemblance. They just sort of represent the perceptual state of affairs. They are they're just symbols for that perceptual state of affairs. And then if some higher cognitive competence must be accounted for, the idea is that there's an algorithm which then somehow manipulates these symbols, for example, to deduce a certain conclusion from logical premises. And that algorithm then generates a result, which is again given in terms of amodal symbols. And then if the conclusion should lead to an action, for example, then that symbolic representation is again transduced back to the motor representations in the motor regions of the brain that allow you to act. And there are many challenges to this view, which have been increasingly recognized in the last 2 decades. So for instance, there's no empirical evidence for algorithmic processing of amodal symbols in the brain. What we find instead is that there's strong evidence that the higher cognitive competences make use of perceptual motor representations and processes. So to give an example, there's a set of studies which compare the activation in different brain regions for different tasks that pertain to a certain object category. So let's say there's a certain brain region that becomes active when you perceive an apple, or when you grab an apple, or do some low-level sensory motor behavior relating to apples, then that same brain region will also become active if there is no actual apple, you're just solving a reasoning problem about apples. And also, if that brain region is impaired, there's also studies for that. So I highly recommend this review by Basalut's paper titled Perceptual Symbol Systems, where a lot of that is reviewed. And there's also a more recent one from 2008 called Grounded Cognition, I think, that reviews a large body of evidence that in tasks where we solve some reasoning problems about or certain object categories, we reuse the same representations and possibly also the same processes that are involved in more primitive cognitive competences having to do with low-level sensation, categorization, and so on, or imagery. Another challenge to this algorithmic symbol processing account is what's famously called the symbol grounding problem, going back to Harnad. It's a bit difficult to summarize this argument on short notice, but just to give you a high-level idea, the problem with this algorithmic account is that it cannot account for the fact that we have a sense of understanding what our reasoning is about. When we think about something, we do not just blindly manipulate symbols according to deterministic algorithmic rules, but instead we have a sense that we understand what that reasoning is about. And this cannot be accounted for by the mere algorithmic manipulation of amodal symbols, which just represent something. Rather, there must be something more going on, which actually uses the kinds of representations that give us a sense for what our reasoning is about. It's not just blindly manipulating amodal symbols. And finally, this algorithmic symbol processing view is inconsistent with neural principles of computation. So the algorithm itself doesn't actually state how the neural networks of the brain could realize that algorithm. So an algorithm assumes that there's some central processor that performs the algorithm, which can actually make use of a random access memory. So random access memory is kind of memory where you can just flexibly insert new memories at an arbitrary location in the memory, and you can also flexibly read out a memory at an arbitrary location. And that is neurally highly implausible. So that would require that essentially that everything is connected to everything in the brain, because if you have a certain processor that has to combine your representation of an apple with a representation of a tree, and has to perform some algorithm that mixes these somehow, then you would somehow have to take the representation of the apple and also take the representation of the tree, and then have them in the processor to combine them somehow. And that would necessitate essentially that everything is connected to that processor. And that is not in line with what we know about how the brain is wired up. And such considerations have then given rise to the hypothesis, which is actually so I'm now framing this hypothesis in a particular way, but I think that this is pretty much in line with how Professor Schöner would also phrase it. And also, I think many of the people in the DFT community believe things that are in line with that hypothesis. And that hypothesis is that higher cognitive competences reuse and extend evolutionarily older perceptual motor representation and processes, rather than being implemented by a fundamentally new kind of process. Right? So the classical computational theory of mind would have stated that at some point in evolution, a completely new kind of process emerged, namely this algorithmic symbol processing, which gives rise to the human intellect. And in contrast, this hypothesis states that no, that's not what happened. Rather, evolution keeps building on things that are already there and reuses them and possibly also extends them. But still, the idea is that the evolutionarily older neural hardware of the brain, which gives rise to more primitive cognitive competences, like the kinds of behavior you would see in monkeys, that neural hardware is already in place, and evolution then builds on that in order to achieve the higher cognitive competences. And in doing so, it reuses representations and processes that are evolutionarily older. And that is then somehow extended, or let's say orchestrated in a particular way that can then account for how we reason, how we understand language or produce language, how we plan, and so on. And another way that this is sometimes framed in the DFT community is that the higher cognitive competences are grounded in these evolutionarily older perceptual motor representations and processes. And a related claim is that these higher cognitive competences don't just come in addition to the other hardware by virtue of new neural principles that do something of a different kind than these perceptual motor representations and processes, but rather that the same neural principles that are already in place evolutionarily for achieving these perceptual motor competences, or more primitive cognitive competences, that they have these neural principles also hold true for whatever comes in addition to achieve the higher cognitive competences. So not only is the existing neural hardware reused and extended, but the extensions also follow the same neural principles as what's been there before. And finally, a part of this claim is that these are the neural principles of dynamic field theory, namely detection, selection, working memory, coordinate transforms, finding through space, and search. And so a research goal in the DFT community is to demonstrate how the higher cognitive competences may emerge from the neural principles postulated in DFT. And possibly not only using the same neural principles, but also reusing the exact same neural populations as the more primitive sensory motor processes. Right? So the idea is essentially that we have these DFT architectures in place that can do certain things that we have already seen, which could be described as something like perceptual motor competences, and to see what has to be changed about this architecture or possibly extended in order to achieve the higher cognitive competences in a way that makes use of these other representations and processes. So the research goal is take these DFT architectures and see how can we achieve the higher cognitive competences. And here's a brief glimpse at the references. And next, I'm going to take you through some of the architectures that have been proposed in this research division. Now, today I want to focus on models of the perceptual grounding of language, which is sort of subsumed by language understanding, which is like a part of language understanding. And next week, I will then present something more on language grounding and also on analogical reasoning. And if we have time, also some mental model formation, which is sort of the grounded cognition way of accounting for deductive reasoning. So what is perceptual grounding? We refer as perceptual grounding to the process of associating natural language with the denoted perceptual representation, right? So we have a natural language phrase, some sentence or phrase, and certain parts of that phrase, certain words, denote certain perceptual representation. So for example, in the phrase, the black swan sits below a tree, the word tree denotes some concept of a tree, or some perceptual representation of what a prototypical tree looks like. And also the word swan denotes something similar for swans. And this is actually just schematic. This is supposed to give you a sense of what essentially could be characterized as the perceptual meaning of the respective word. Something like a blend or prototype, a prototypical member of the respective category, right? Category of swans or the category of trees. And also for the word black, we have something similar. So some perceptual representation that characterizes what a black object looks like. And finally, we have such things also for, not finally, so we also have it for relationships. So the word below denotes some concept, relational concept of belowness, for what it means for an object to be below another one. And there's a certain DFT way to spell that out, as we will see. And finally, we also have verbs that stand for action concepts, and that's actually hard to draw, so there's nothing here for sits, but we have some perceptual representation and also motor representation of what it means to sit, for example. Yeah, so in general, all of the words in the phrase somehow have a certain perceptual meaning, which is a representation of some action or property or object category or something else entirely, depending on, so if we introduce more complex language later into the mix. And another thing that's necessary to understand a phrase is to also identify, so in the case of noun phrases, which are phrases like that describe an object, like the black swan that sits below a tree, there's a certain referent of that phrase. So if somebody tells me, look at the black swan that sits below the tree, then my understanding of the phrase requires also that I attend to the spatial location of the denoted object. So if I look at a certain scene here, then my understanding includes not only associating the words with concepts, but also then finding the object that's been described here. So both of them together could be characterized or subsumed under heading perceptual grounding of language. Because we have a language with a phrase that somehow just uses discrete words, and perceptual grounding entails essentially these two things. So associating the words with their perceptual meaning and finding the object that's described by the whole phrase. And this is a necessary step towards models of language understanding. I wouldn't go so far to say that that is all that there is to language understanding, but it's definitely an important component, because in communicative situations, we can only understand what the speaker means if we understand both the concepts that are denoted by the individual words, and we are also able to attend to the object that the person is talking about. Yeah, so we call then perceptual grounding the process of, so given a natural language phrase, perceptual grounding is the process of associating the words with concepts and finding the denoted object in the visual array, right, in the visual representation of the scene or the perceptual input coming into our senses. And there have been multiple models in the last 10 years along these lines, all of which build towards a more comprehensive model of perceptual grounding, step by step. And the first work along these lines is a model by Lipinski et al. And that 2012, so that's the reference here. That starts with what they refer to as spatial language. So, like I said, the perceptual grounding of language more generally is too ambitious to immediately address it, but rather you have to build towards that step by step. And so, since it's particularly, since spatial relations are particularly accessible to the DFT models that were in place already, like the ones you have learned about already for coordinate transformations, visual search, and so on. The spatial language lends itself to a DFT account. So that's the main motivation why the DFT community has started with the grounding of spatial, with building models that ground spatial language, right? So we take certain DFT models, visual search, coordinate transformations, and some additional things that will be added, which we'll see later. And we show that this architecture, which actually stems from, which could be said to be evolutionarily older, because it's already necessary merely for perception and action without any higher cognition, thinking, or language understanding going on. But the idea is, as we said already, the idea of grounded cognition is that these neural architectures, which are already in place before language, which were evolutionarily already in place before language evolved, they sort of are the means by which language understanding emerged. So that the evolution essentially reused those existing representations and circuits and built on top of that in order to enable communication through language. And so the idea now is, how can we take the DFT principles that we know of already and that we know to have existed evolutionarily prior to the emergence of language, and build essentially a model that can account for how we understand simple spatial language. And spatial language, maybe I should have started by saying that, is essentially language that involves spatial terms. So terms that have a concrete perceptual meaning. So this relates primarily to spatial relationships. So an example for a phrase that we might refer to as spatial language is the phrase that says the green object, which is to the left of the red object. And that lends itself to a DFT account because we know how to visually search for objects with a certain color by DFT, or rather how we know how the brain plausibly does it. And we also have coordinate transformations at our avail, which gives us an idea for how spatial relational language can be grounded by virtue of these coordinate transforms. And yeah, other relationships which might be considered spatial relationships as well are things like in front of, inside, on top of, and so on. So yeah, so the first architecture that I'm going to present now is the cognitive architecture for grounding simple spatial language. So language that just includes two object descriptions and a single spatial relation. And the architecture then grounds that object description. And that architecture is actually possible to perform multiple cognitive tasks pertaining to spatial language. One of them is a spatial comparison task. So the idea is when the model is sort of presented with a query like, where is the green object relative to the red object? Then we want that model to respond that it is to the right. And this is not yet, strictly speaking, a grounding task. The grounding task will come in later, but I'm going to start with this because the model that enables this can then later be extended to also enable grounding, as we will see. So that was just as a motivation. So essentially, I'm now going to present a DFT architecture that can, amongst other things, answer such questions like, where's the green object relative to the red object? And given a certain visual input, it then may give a correct answer to that question, in this case, to the right. Yeah, the green object is to the right of the red object. And it's also able to do some other tasks, which I'm going to address afterwards. So there are certain operations required in order to solve such a spatial comparison task with the means of DFT. The first one is to find the described objects in the perceptual input. Yeah, so before we can answer where is the green object relative to the red object, we have to find both first the green object, then the red object, and then we can sort of test or determine which spatial relationship holds among these objects. And in such queries, we refer to the first object whose location we're interested in as the target object, and to the second object relative to which we want to know the target location as the reference. Yeah, so the green object is relative. Where's the green object relative to the red object? Green object is what the one whose location we're interested in. That's the target object, and the red object is the reference object relative to which we want to know the target location. So after having found the objects in the perceptual input, we need to perform a coordinate transformation in order to get the position of the target object relative to the reference object. Yeah, so we want to get the position, in this example, we want to get the position of the green object relative to the red object. So we would want some representation in a field in relative coordinates. And finally, we do not just want the model to answer with the relative spatial location, but we want it to answer with a spatial relational term or concept. So the answer should be, it's to the right. And so what we need to do is we need to compare that relative position to a certain spatial relational template. So for example, if the relative location, I have to show it from your perspective, look at my camera, if the spatial location is here, that my hand is the center, then that would match the right of concept, because that relative location corresponds or is correctly described as to the right. And any location on this line that I'm now drawing with my hand would also be matched to the right of concept, and possibly also locations which are slightly off, that would also be to the right, but maybe not if it's too high. Then under some definition it might still be on the right, but under another definition it's not really to the right, because the right would be more to the point here. And analogously, if the relative location were like this, we wanted to respond it's to the left. And if it were here, we wanted to respond, that's now the x-axis here. If the location were here, we wanted to respond it's on top or above, and here would be below. Yeah, and these are all the spatial relations that we're going to address in this model. Because that's the first step, and the subsequent models gradually extend this architecture, introduce more and more vocabulary, essentially, to account for more and more language grounding. So the first step, like I said, is finding objects in the perceptual input. So this is this on top here. This actually, these show the same architecture at two different points in time. And that's not yet the whole architecture. I'm just showing a relevant subpart of the architecture right now. On top, we have this regular, simple visual search mechanism that's just a single 3D field defined over the two spatial dimensions of the visual input and an additional color dimension, and thereby enables visual search by providing slice input into the respective region, right? So if you disregard for now that here this currently receives boost input, you see that the red object provides subthreshold input in the red region of this field, right? So these are actually 2D snapshots of 3 different slices through the 3D field. So in the red region of the field, we have the spatial map of that gives us the location of the red objects. The green region, we have the spatial map that gives us the location of the green objects, and the same for the blue object. And this enables visual search by providing a boost input to the respective slice or region, and thereby causing the formation of a peak at the spatial locations of objects with that color, right? So if we provide a boost input into the green region of this color attention field or color space attention field, as it's sometimes called, then that will cause a result in the formation of a peak at the location of green objects, and the same for the other colors. And additionally, we assume that there are so-called concept nodes. Yeah, so we have a red concept node, a green concept node, and a blue concept node, and they project into the respective region of the color space attention field. So by activating these neural nodes, the slice input is provided into the respective region. So by activating the green concept node, we have slice input into the green region of this 3D color space field. And so in effect, activating the green region causes peaks to form at the location of green objects. And all of these, or the whole field, projects both to a target field and a reference field. These are both 2D fields. And they do not, this input is not yet enough to induce a peak there, but an additional boost input has to be supplied. So if we want then to first find and store the location of the target object, which is green in this example, then we simultaneously activate the green color concept node and provide a boost input to the target field, and that will cause a peak to form in the target field on the location of the green object. And afterwards, if we want to also store the location of the red reference object, we subsequently simultaneously activate the red concept node and boost the reference field instead, and that will then store a peak on the location of the red reference object. And both of these fields are self-sustained, so that when the concept nodes are deactivated, the location of the target and reference are sustained in these fields. So that was that essentially means finding the object in the perceptual input, finding the target object and the reference object, and remembering their location in a short-term memory, which is necessary in order to subsequently compare their, or rather determine the relative location of the target object in a coherent system that's centered on the reference object. And why do we need to do this in sequence? Simply because the visual search mechanism cannot simultaneously search for two objects at the same time. So it's not consistent with data to assume that there's two visual search mechanisms where you can find the green target object and the red reference object simultaneously in parallel and store the result in the respective fields. Rather, you can only search one object at a time. And so you first search, in this example, the green green target object and boost the target field so that the result of the visual search is stored in the target field. And subsequently, you search for the red reference object. So as I said, the next step is to transform the location of the target into a coordinate system that's centered on the reference object. And this is just the neural coordinate transform that you have learned about in the lecture on higher dimensional fields, I think. And the output of this coordinate transform fields into an object-centered field. Yeah, so that's just another 2D field, which then contains the location of the target object relative to the reference object. So since here the target object is to the left of to the right of the reference object, we have this peak here, right? Relative location is to the right of the center. And the last step is to compare that relative position to a spatial template in order to be able to answer the question, where's the green object relative to the red object in terms of a concept or word that describes a relation. And for this, we need to introduce concept nodes. These concept nodes receive input from the object-centered field. Actually, every concept node receives input from the whole field in a sense, but according to synaptic weight patterns, which are given as these spatial templates, right? So for example, the right concept node that receives input from the object-centered field, but not all locations in that field provide the same level of input to the node, but rather different regions of the field have a different synaptic weight, which means that the output at that location in the field is multiplied by that synaptic weight pattern, and the result then feeds into the concept node. So this means that if you look at this pattern here, this essentially means those peaks in the object-centered field that are in the more red region, which means higher synaptic connection weights, would provide more input to the right node than those locations in this blue region, which means low synaptic weight, right? So this is the color code. This means high synaptic weight. This means low synaptic weight. And in effect, what this does is, if a peak in the object-centered field matches this spatial template well, then there's a lot of input to the concept node. And if it doesn't match it well, then there's less input. And we can see in the activation of these 4 nodes that the right of node, in fact, receives the largest amount of input and therefore has the highest activation. And that's simply because this relative location perfectly matches the right of spatial template. For the other nodes, the input is rather low because it's neither to the left nor above nor below. And perhaps just to give you a sense of what this means mathematically, so you know that the field has an output, and when the field projects through a node, that output is summed over the whole field, but different locations. So that's essentially the mathematical way to model that every location in the field has a synaptic connection to the node, but some locations have stronger connections than others. And stronger connection means that if there is an output at that field, then that causes more input to the node than if it had a lower synaptic connection strength. The field forms a peak, and there's a certain activation there, and the output at that location is multiplied by the synaptic weight of the synaptic connection from that field location to the node. And since these spatial patterns essentially determine what that multiplication factor is, what the synaptic strength is. And therefore, if the overlap between the relative position and the spatial template is large, the node gets high activation. And if it's low, the node gets low activation. And this effectively then compares the relative position to a spatial template in a neural dynamic architecture. Yeah, there are some other tasks that this architecture is able to perform, but I don't want to address these now. I want to come back to the. So if you're interested in these, you can have a look at this Lipinski et al. Paper. Just as a quick summary, it can also solve a target identification task in which the question is which object is above the blue object, right? So you only specify the spatial relation concept and a reference object, and then it should respond with the color of the target object. And that essentially just runs the same architecture backwards. So all connections are in every direction, actually. And therefore, it can also answer such queries. And similarly, it can also answer the question, where's the green object? And the model would respond with both the location, the color of a reference object and a spatial relation concept, which means, yeah, it's to the left of the blue object. But what I want to focus on is really the grounding paradigm. So the grounding of a phrase which describes an object, as I said already, means finding the described object in the visual input. So for example, if the phrase is the red object to the left of the green object, which actually describes a certain object, then grounding that phrase means finding the object and attending to its spatial location. And this is not yet solved by the Lipinski model because it requires a form of hypothesis testing. And this can be made apparent by looking at this example. So if we want to find the red object to the left of the green object, we do not yet know what the green reference object is because there are two possibilities. Could be either this one or that one. So if you first find the reference object, select it and store it in the reference field, and then try to find a red object which is to the left of that, then we might end up not finding one because we accidentally selected this wrong green object. And what we need then is a possibility for the model to undo its selection decision and then select the other green object. So in case it doesn't find a red object to the left of the reference object that it has considered as a candidate, it has to reject that hypothesis and make a new hypothesis about what the reference object is in order to then check again if there's a red object to the left. Another desideratum of this extension to the model that I'm about to present is autonomy. So we've seen that the Lipinski model requires that the user activates appropriate nodes and provides appropriate boosts at certain moments in time. So in other words, the user doesn't just specify the phrase and then the model autonomously finds or answers the question, but really it consistently relies on input by the user at correct moments in time. And the new model that I'm going to present doesn't require that. So that model, in that model, the phrase is simply specified just once in the beginning. It's encoded as an activation pattern over self-sustained nodes, which then encode the phrase, the red object to the left of the green object, for example. And subsequently, the model just completely autonomously finds the described object, and it completely autonomously performs the required hypothesis testing. And this is a figure of the model. So this model is by Richter, Linz, and Schöner, 2014. And I'm going to briefly or slowly take you through the different components of the architecture. And this is actually a good example of the more, you could say, cognitive side of things, because this model incorporates a lot of the important key extensions to classical DFT, which are required to actually build autonomous cognitive architectures. So they include things like process organization, where different processes exist that autonomously orchestrate the different components of the architecture. They include the conditions of satisfaction and so on. So we'll look at the different components, and just let it be noted that while going through the architecture, I will introduce a few new concepts. And here, this is just an example, but these concepts are actually useful quite generally, and they are used in very many cognitive architectures. So as before, we have color concept nodes, but this time we introduce two sets of color concept nodes, one for the reference role and one for the target role. And that is because we want to already encode the entire phrase beforehand, right? So we want to tell the model beforehand what is the color of the reference object and what is the color of the target object. And that should then be stored in self-sustained nodes, and everything else should happen autonomously. And so we need one node that keeps, or one set of nodes that can be used to keep the color of the reference object in short-term memory, and another set of nodes that allows to keep the color of the target object in short-term. These are the blue set of nodes. We call them memory nodes, color memory nodes. And we have the same thing for the spatial relational concepts. So we have these blue spatial relation memory nodes. And so all of the blue nodes together can be used to encode an arbitrary phrase, like red to the right of green, or orange above blue, or whatever. So that's all the user has to do. They specify the query by activating these nodes. And then subsequently, the whole architecture completely autonomously finds the described object. For example, the red object to the left of the green object. And yeah, there are various components to this architecture, some of which you're already familiar with, hopefully. So the visual search mechanism is like a simplified version of what you have seen already. So there's a perceptual field defined over two spatial dimensions and a color dimension. And that field can be used to find objects. These fields I'm not going to address now, but they essentially allow the model to detect whether an object with a certain color has successfully been found. A major novelty in this model is what I referred to already, a process organization system. So in this in the more recent DFT models, there's a particular way in which or a particular theory about how processes are realized in neural dynamics. So every process has a so-called intention node and a condition of satisfaction node. So the intention nodes are these green nodes here, and the condition of satisfaction nodes are these red nodes here. We have a process called the spatial turn process, another process called the reference process, and yet another process called the target process. The reference process is essentially becomes active when we want to find the reference object of the phrase that we have encoded in short-term memory. The target process becomes active when we want to find the target object of that encoded phrase. And the spatial turn process essentially just immediately becomes active because AI just serves to essentially activate the relational comparison machinery. And yeah, so the attention node of a process more generally, that is essentially the node which characterizes whether, or which represents whether or not the process is currently active and able to exert an influence on the architecture. And the effect that a process has on the architecture is given by the synaptic connections between the intention node and the fields of the architecture. So depending on what the process is supposed to do in the architecture, it will connect to certain fields in order to achieve its desired behavior. And the condition of satisfaction node generally serves to represent that the process has successfully done what it was supposed to do, right? So that's why it's called a condition of satisfaction, because there was a certain intention that was supposed to be performed, and when that intention is satisfied, or under the condition, or under certain conditions, that intention is satisfied, and if this is in fact these conditions hold, the condition of satisfaction node is activated, which then causes the process to finish. So the condition of satisfaction node inhibits the intention node and thereby deactivates the process, right? So process becomes active, it does something, and then under certain conditions, it's clear that the process has done what it wanted to do, or what it was supposed to do. And if that holds, then the condition of satisfaction node becomes active and results in the deactivation of the intention node. And this abstract way of describing it is perhaps made more clear by examples. So let's look at the reference process. So the purpose of the reference process, like I said, is to trigger the search for the reference object and store it in the reference field, right? So here we again have a reference field, like in the Lipinski model, that's supposed to hold the spatial location of the reference object. And this process becomes active by default. In the beginning, when the architecture is run, that process just becomes active. And what this process does is determined by the connections from the intention node to the various nodes and field of the architecture. In this case, the first thing it does is it provides a boost input to the reference field, thereby bringing that field into a dynamic regime where it can form peaks. And this way, if we now trigger a visual search for a certain object, the result of that search can be stored in the reference field. If it didn't provide that boost input, then it would not, then the visual search, the output of the visual search wouldn't provide enough input into the reference field in order to enable the formation of the peak, right? So that's why this boost input is necessary. And to immediately give the other example, the target intention analogously projects to the target field. In this case, it's called the target candidates field. I'll later address what that means. And so if the target process is active and a visual search is triggered, the locations will instead be stored in the target field, not the reference. So coming back to the reference process, the second effect that this intention node has is it provides input to these purple nodes here, which are called color production nodes. And these nodes receive additional input from these memory nodes that encode the color of the reference object as supplied by the user, right? So the blue nodes encode the reference color of the mentioned in the phrase. That's one input into the purple nodes. The other input is input from the reference process intention. And when these inputs coincide, the purple node forms a peak. So effectively, if we have this green color memory node active here, and also the reference process becomes active, then and only then does this purple color production node form a peak. And this is necessary because we only want to trigger a search for an object with the reference color if the reference process is active. And this purple node then projects to the visual search system in order to actually find a search for an object with that color. In this case, a green object. And these sets of nodes here implement the analogous thing for the target object. So if the target process intention becomes active, then it will provide input to these purple color production nodes. And if that coincides with input from a color memory node, so if, for example, the target object is blue, then this node, memory node would be active, and this node would then become active after that intention node became active, and that would then trigger the search for a blue target object. In this way, we can, first search for the reference object stored in the reference field, then search for the target object stored in the target field, or rather not we do it, but the architecture does it autonomously. Down here, we see a similar architecture as the Lipinski et al. Model. So the reference field and the target field together provide input into a coordinate transform, which transforms the location of the target candidates into a coordinate system that's centered on the reference object. And the result of that field feeds into a relational condition of satisfaction field, as it's called here. And that field receives additional input from the spatial term nodes. And it forms peak where those two inputs overlap. So effectively, it will form peaks on the locations of those target candidates which stand in the given spatial relation to the reference object. So yeah, that's essentially it. So that's like the reverse thing of what we've seen in the Lipinski et al. Model. The nodes project to the field, and these synapses, so every one of these spatial term nodes or spatial relation concept nodes projects to all the regions in the relational field where the synaptic weight patterns correspond to the spatial templates that we've seen already. And this way, by activating the spatial term nodes, the relation field is pre-shaped by that spatial template. And if that pre-shape overlaps with the actual, with the actual relative locations of the target candidates, the field forms a peak. So the formation of a peak essentially means that there is a target candidate which stands in the correct spatial relation to the reference object. And yeah, what's new here is that the target candidates field may have multiple peaks, but that's just a minor detail. So that's just the assumption that there can always be multiple target objects, all of which should simultaneously be compared to the spatial template. Yeah, and another novel thing is that we also have a relational condition of dissatisfaction field. And that essentially serves to detect whether no peak formed in the relation field, or in other words, whether the relative location of the target candidates does not match the activated spatial relation concept. And this is achieved simply by providing the inverse spatial relation pattern. So the synaptic weight pattern is the inverse template as the actual one. And so that field will form a peak if, in this example, the target candidates are not to the right of the reference object. And yeah, the final thing or ingredient that we need to understand this architecture are the various conditions of satisfaction of the processes. So if the relational condition of satisfaction field forms a peak, it means we have found a target candidate which stands in the given spatial relation to the given reference object. And that essentially means we have grounded the phrase. We know the object that is described, correctly described by that phrase. For example, red object to the left of the green object. We have found that. So that will activate the condition of satisfaction of this spatial term process. So the spatial term process, essentially, it just activates these production nodes of the spatial terms and provides input. It provides these spatial pre-shaped inputs into these two fields, and that's what the effect of its intention node. And its condition of satisfaction is that a relative, an object with that which matches that spatial template has been found. The reference process has as its condition of satisfaction the formation of a peak in the reference field, which just signals that an object that the reference object with the desired color has in fact been found and stored in the reference field. And the condition of satisfaction of the target is analogously given by the formation of peaks in the target candidates field. So if the condition of satisfaction is true, that we're just finished, and we have grounded the phrase. But it might happen that we have not found a target candidate which stands in the specified spatial relation to a reference object, which might, for example, if we go back to this example here, this might be the case if we have accidentally or wrongly selected this as our green reference object, and then we're not able to find any target candidates which are to the left of that green object. And so the relational condition of satisfaction field would not form a peak, but instead the relational condition of dissatisfaction field would form a peak. And when that happens, which is unfortunately not plotted in this figure, I think that it would just delete the target candidates and the reference field. So it would just inhibit the reference field and the target candidates field, thereby causing the peaks to decay. And in effect, this causes the condition of satisfaction of the reference process and the target process to become deactivated, and therefore the intention nodes can become active again. And so the search for a new reference object would start. And in order to prevent the same reference object from being selected more than once, there is an inhibition of return field, which receives input from the reference field and is self-sustained. And also it inhibits the reference field, preventing it from becoming active, from selecting the same object again. So in the second round, another reference object would be selected, and so on. And if there are many reference objects, then over time, the architecture would autonomously try each of them until it has found one where, in fact, target candidates could be found that are in the correct spatial relationship to the reference object. And when that happens, so when this relational condition of satisfaction field forms a peak, that is also then fed back or transformed back into the absolute coordinates and provides input into a target response field, which effectively forms a peak on the location of the target in absolute coordinates. Yeah, I think I've addressed all of the architecture. Let's now look at a simulation example where the phrase is the red object to the left of the green object with this example image that we've seen already. And what we would expect is that it might accidentally or wrongly select this as the reference object. It might then check whether the relative locations of the red target candidates to the reference object match the left of pattern. It would detect that this is not the case, and it would then subsequently select a new reference object and again check whether these relative locations are in fact or match the left of spatial templates. And that would in fact be the case, and so the architecture would finish and report that this here is, or rather it would form a peak in the target response field on this object here, representing that the the phrase has correctly been perceptually grounded because we have found the red object, which is to the left of the green object. And here we see simulation results of this architecture. So up here, we see the time courses of the different nodes, of the intention nodes of the different processes, spatial term process, the reference process, and the target process. And here we see snapshots in time of the various fields of the architecture. So every column is one snapshot in time, denoted here as T1, T2, T3, T4, and so on. And every row is a different field. So initially, the spatial term process and the reference process become active. There's actually one more thing I didn't explain, namely, we do not, so as I said, the search for the reference and target cannot happen simultaneously, but only in sequence. So we do not want the reference and the target process to become active at the same time. And in order to prevent this, we have a so-called precondition node, which inhibits the intention of the target process, thereby preventing it from becoming active. So by default, then only the reference process would become active. And if once the condition of satisfaction node of the reference process has become active, which means the process has finished, it will inhibit this precondition node and thereby release the inhibition. And this will then allow the target process node to become active. And the last thing I should mention is that all process nodes consistently receive boost input. So by default, they would become active unless they are inhibited, like in this case, for example. And that's why by default, only the spatial term process and the reference process intentions become active here, whereas the target process is not active. And what the reference process does is it boosts the reference field, and it also causes the green color production node to become active, which triggers a visual search for green objects. And in effect, the location of the green object is stored in the reference field. And that will activate the condition of satisfaction of the reference process. And subsequently, we see that here, so because the condition of satisfaction is active, the reference intention node gets inhibited, so it gradually gets deactivated. And subsequently, the target process intention becomes active, this red curve here, which provides boost to the target candidates field and causes or triggers a visual search for red objects. And in effect causes the location of the red objects to be stored in the target candidates field. And we also see that meanwhile, the spatial term node has also been active and has caused the relational condition of satisfaction field to be pre-shaped with the spatial relation pattern, and the relational condition of dissatisfaction field to be pre-shaped by the inverse spatial relation pattern. And what we see is that since this is the reference location that we have selected, and these are the target candidates, we see that this matches with the relational condition of dissatisfaction, or rather with the inverse spatial relation pattern, because the target candidates are not to the left of the reference object. And therefore, the condition of dissatisfaction field forms peaks, which effectively causes the deletion of the peaks in the target candidates field and in the reference field. And since this now removes the condition of satisfaction of the reference process becomes active again. And it again triggers a visual search for green objects. And we see that the reference field now forms a peak again, this time on the other green object, because the inhibition of return field here has inhibited the previously selected location, thereby causing the reference field to select a new reference object. And again, here, afterwards, the target process becomes active, again storing the red target candidates in the target candidates field, and again the spatial relation field has this left-off pattern as its pre-shape, and since this pattern in fact matches the relative spatial locations of the target candidates, we see that this relational field forms a peak because these two target candidates are in fact to the left of the selected reference object, and so the relative coordinate matches the spatial template, and therefore the field forms a peak, which in turn activates the condition of satisfaction of the target field and results in the formation of a peak on the absolute location of the target in a target response field. Yeah, so we have seen that so the formation in the target response field essentially signals that the phrase has successfully been grounded. So this demonstrates that this architecture is in fact able to ground arbitrary spatial phrases composed of color terms and spatial relation terms. Now, to drive home the point that I made at the beginning of this lecture, I've presented a neurodynamic architecture that can ground simple spatial language composed of two color terms and a spatial relation term. And that is, of course, only a small subset of all the kinds of things that could be said with language. But the principles that were used there, they can actually be extended towards a much larger vocabulary that also involves other kinds of adjectives and other kinds of relationships, both spatial and also more abstract, as we postulate. And that architecture has been built using the neural principles formalized in DFT, and does in fact build on perceptual motor representations and processes in accordance with the grounded cognition stance. So it's built out of neural fields with the various instabilities. It employs coordinate transformations using the same neural mechanisms that are also used in reference frame transformations of non-linguistic cognitive capacities. Like, for example, I think we have seen some examples for that in the lecture on coordinate transforms. It also employs model of visual search that is also hypothesized to be evolutionarily older, and it employs a notion of concepts that are characterized in terms of synaptic connections to a color field or a spatial relation field. And all of these are necessary steps towards language grounding architectures more generally, and consequently necessary steps towards language understanding architectures, which are consistent with the grounded cognition stance. Next week, I'm going to present some extensions to this architecture that can ground verbs and also grammatically complex sentences. And all of this is part of a research goal that is sort of the topic of my PhD thesis, to achieve compositionality with DFT. So in this grounded cognition paradigm, we want to be able to achieve compositionality, which essentially means that we want to account for how we understand the meanings of sentences or phrases by understanding the meanings of the individual words and combining those meanings in accordance with how the words are arranged syntactically in the phrase or sentence. And that is actually the hallmark, in a sense, of the human language capacity, which enables us to communicate so flexibly about our environment. And also in thought, there's also believed to be compositionality, which enables us to think so flexibly about our environment and reason so flexibly by virtue of combining concepts with each other to create complex combinatorial concepts, if this formulation makes sense somehow. Yeah, and that will actually be the main part of next week, but I also want to give a glimpse at some other work that has been done in the grounded cognition tradition. One of them is a deductive reasoning model, which employs what's referred to as mental model formation. So that's a model that can account for how we can make logical inferences in particular deductive reasoning paradigms. So given a certain set of premises, we can infer a conclusion. And that is actually implemented by mental models that are, again, supervenient on the same neural architectures and neural mechanisms of more low-level perceptual processes. And now also give you a glimpse at a model of analogical reasoning, where essentially knowledge about one scene is transferred to knowledge to another scene, which is analogous to the first scene in some sense. So more particularly, I'm going to show you that part of the architecture that can identify an analogy between two scenes, where, for example, if both scenes depict a triangle above a rectangle having the same color and a different size, but the two scenes look dissimilar superficially, still the model is able to detect an analogy. And that is, again, supervenient on many of the mechanisms that we have already seen. So I thank you for your attention, and next week there will be another